ask biologists what the most important molecule is to life, most of them would say water. Without water, there is no life. And we don't just mean there is no life here on Earth. We believe that there is no life anywhere in the universe without water. So what is it about water that makes it so essential for life? And how do we regulate it in the garden if it's such a key ingredient? There are many properties of water that makes it a unique substance. But if I had to choose one thing that makes water essential to life, it's its solvent properties. Water is known as a universal solvent, and that is an important feature of it. Biological systems are complex chemical reaction systems in many ways. It's a biochemistry of life is what you're looking at when you look at an organism. And in order to have such complex, rich chemical reactions, you are going to need a complex set of ingredients. But according to the collision theory, reactions only occur when reactants collide with sufficient energy and the correct orientation. That means that the reactants are not likely to do that when they're in solid form, because solids are not very mobile. The molecules are locked into lattice structures, so you don't want it to be in a solid form. That means it would have to be in a gaseous form or a liquid form in order to have a meaningful number of reactions. The problem with gases, though, is that gases fill whatever space they have, and so the molecules become very distant from each other. So the ideal phase in which life can occur is going to be a liquid form. The problem is that any given temperature for any planet, only a percentage of molecules would be in liquid form. Every molecule has its boiling point, its melting point. And you have to be between your melting and boiling point in order to be a liquid. Only a small number of molecules will ever be there. But what if you had a solvent? A universal solvent, one that could dissolve most molecules. Then so long as that solvent is in a liquid state, like it is on this planet, then all the other molecules that you need could simply dissolve into it and be as though they were in a liquid phase. They are. They're in a soluble phase. They're in an aqueous phase, we say. So water is essential because it dissolves all of the things you need in order to have the chemical reactions that are associated with life. So if you do not have water, you will not have life. That is becoming a real challenge in the sustainable garden. Much of our plants in our gardens, the one we desire, require a lot of water. More so than some of the plants we don't desire, like weeds, etc. The plants we desire tend to be high water usage plants. And not all of us live in areas where we have a large supply of rain, naturally occurring water falling on the garden. And that can be problematic. So first, let's understand what is happening in a plant, how the water moves through the plant, and then how we can regulate it in the garden so that we minimize the amount we need to pour onto the garden, and understand how some of the changes that are going on globally with climate change are going to add to the strategies, the challenges that we're going to face, as it were, in the garden. So to do that, we're going to take a look at an Echinacea plant right next to me. This is a clump of Echinaceas. I started this cluster with I think I put 2 tiny plants in, and as you can see, it has spread beautifully. It is a plant that needs very little. It is a native plant. There are a variety, I think 2 varieties in here. One I think is the native version and one is a hybrid version, but they're very similar. It's hard to tell them apart, to be honest. And they do very well in heat, in dry conditions, because they're adapted to this location, and they are great pollinators. Right now it's fairly cool and there's not a lot of pollinators out, but later today we will see them. So when we look closer at the plant, it rained last night. So we can see that on the plant surface, there are beads of water. Why does this occur first? Because understanding why water beads and then how it behaves is going to be key to understanding how it moves through the plant. Water is a polar compound, a polar covalent compound. That means that technically the molecule has no charge components to it. There are no cations and anions. It is neutral. The electrons in the bonds are shared, but the sharing is not equal. Water is composed of oxygen and hydrogen. Oxygen has a high electronegativity, which means it tends to pull electrons closer to it, compared to hydrogen, which has a much lower electronegativity. So what happens is that even though the bond is a shared bond, water actually has areas where it is slightly positively charged. Not a full positive charge, but it's slightly positive, and other areas where it's slightly negative. The oxygen has a slight negativity to it, and the hydrogen has a slight positive charge to it. And what that means is water molecules are actually attracted to each other because opposite charges are attracted. So the hydrogens on one water molecule, which are slightly positive, are magnetically attracted to the oxygens on another water molecule, which is slightly negatively charged. So that means that water can form what we call hydrogen bonds. There are weak magnetic attractions between the hydrogens and the oxygens between completely different water molecules. And that means water has a high attraction to itself. But it also means that any molecule that is ionic and carries full charges, like salts, or any molecules that is also polar covalent, can in fact slip between the bonds of water, between different molecules of water, and play a similar role. And the water will basically create a hydrosphere around it, where if it's an ion and the ion is negatively charged, the hydrogens of the water will orient themselves around and form a bubble, essentially, like a circle of water around that ion, and keep it suspended in itself. So the ability of water to dissolve things is because it is a polar covalent molecule. It's not ionic and charged, because if it were ionic, it could only dissolve other ionic things. And often ionic things do not dissolve other things because they are so tightly attracted to each other. It's a full charge going on there. If it were covalent, it would only be able to interact with other purely covalent substances. But water is sort of in between those two things. It is polar covalent. Slightly negatively and positively charged areas exist on it, and that allows it to be flexible in what it dissolves in. It also means that since the water is attracted to itself, it can do some pretty unique things. It clings to itself, and that's why we see it forming beads on the plant. In fact, I'm going to show you a little bit. I just noticed while I was kneeling here, there's some spider webs on the ground here, and we'll see how beautifully, it's actually very pretty how water can bead. So down here you can see that the thyme is covered with a bit of a cobweb, and since it rained, the water is forming beads around it. Oh look, there's a spider crawling all around it, and the spider's crawling. Well, I'm going to move out of the way so I'm out of the spider's way. Yeah, so we disturbed the spider, but you can see his web is coated in little beads of water. Okay, that means that the water isn't actually able to dissolve into the spider's web. It means that the spider web is actually a hydrophobic substance. It can't dissolve into the water, but the water beads upon itself and forms these bubbles on the surface. That means that when we look at the plant and we see that water also beads on the surface of the leaves, it means that the surface of the leaves must be coated in some sort of waterproof layer. It's hydrophobic on its surface. And that's because it usually has some sort of waxy or oily layer on the surface. If I turn the leaf over, however, now I know the bottom did not, but if you notice, it's a much it's a duller surface. If you feel it, it doesn't feel as waxy. And if I were to put water on it, let's just dip some water. I'm going to pull off a leaf. Sorry, I know I'm tearing you. And we're going to dip it in some water. Can I put it in some water? I'm going to get some. All right, so I left the wheelbarrow out last night and there's still some water in it. What we're going to do is just drop the leaf in and play around with it in the water. All right, so this is the top of the leaf. Let's pull it off. You can see that there's lots of beads on top of the surface. Let's do it again and look at the bottom. You can see it's quite wet, but you don't see as many beads. It's as though the water clings to it on the bottom. Do the top again so you can see the difference. You can see there's dry areas and wet areas, and you can see the beads of water. Bottom again, it's more like the water coats it completely. What that tells me is that the bottom of a leaf is different from the top. So the question is, what's so fundamentally different about the top of a leaf and the bottom of a leaf? The top of the leaf is facing upwards to the sun. It is catching all of the sun rays, which means it's also heating up quite a bit. And so water would be easily lost from the surface if it weren't coated with a protective layer. So the surface, the top surface of a leaf is usually coated with a waxy layer. But the bottom of the leaf has to serve a different function. It is the cooler side of the leaf, so it's not going to get heated as much, although granted, a leaf is thin and so it will still get heated quite a bit when it's full sun. But a plant has a problem. It doesn't just need sunlight to live, it also needs carbon dioxide and oxygen. And specifically when it is photosynthesizing, it is going to need to suck carbon dioxide out of the atmosphere. And it's going to need to do that photosynthesis in its primary photosynthetic structure, which is the leaf. So it has to have a way for carbon dioxide to come into it. And that's where there's going to need to have little holes in the leaf. And those are going to be at the bottom, because you'd like to keep your holes away from the sun because you're going to lose too much water. So the top of the leaf is an impermeable barrier to water. It is usually a bit waxy. The bottom of the leaf is not going to be about waterproofing, but about allowing carbon dioxide into the leaf. And it's got these little holes known as stomata. So long as the plant is healthy, the stomata and well hydrated, the stomata are kept open so that carbon dioxide and oxygen can diffuse in and out of the leaf readily. If the plant is wilted, however, the cells around the stomata, known as the guard cells, tend to collapse. The stomata closes, and then water loss is shut down. But photosynthesis is compromised because you're not getting fresh carbon dioxide in it. So ideally, you would like to keep those open as much as possible. So they're on the underside of the leaf, where only when the plant is overly stressed would they close, and you'd minimize the loss of water. So that explains why the leaf is different on the top and the bottom. Now, ultimately, water in plants tends to come from the soil, from the roots, up to the leaves. The reason that can happen is because of that polar covalent nature of water. Since water is attracted to itself, as water evaporates from the leaves, the water molecules there are pulling and tugging on water molecules behind them. And so they pull the water molecules up towards the surface of the leaf. The ones in the leaves are pulling on water molecules further back behind, and so forth, all the way down to the ground. The water pulls itself up against the force of gravity through its magnetic attraction with each other, and it is ultimately driven by the evaporation from the leaf surface. This is known as transpiration. So the water that is coming through a plant comes through the plant from the ground in the roots, up through the plant, and it leaves through the leaves, through the stomata. So in other words, to have a plant healthy, you need to provide it with enough water at its roots so that as water is being lost through the leaves, there's a continuous supply of water coming up through the plant so that the stomatas don't collapse and that photosynthesis is not going to be shut down. So let's take a look at the roots. Look at the roots. What we're going to have to do, unfortunately, is rip out one of my Echinacea plants. And that's okay. I was intending to prune back these Echinacea plants. So what we're going to do is do something I normally don't like to do. We're just going to yank this guy out. Give me a second. I'm going to have to put down my cell phone today. I am intending to buy a tripod for this cell phone, but I haven't gotten around to it yet. So you'll have to take my terrible filming. This is the roots of the Echinacea plant. I'm shaking out the soil. You'll see. You notice that some of the roots are really thick and some are very fibrous. Okay? And that makes sense. They're almost like tiny drinking straws. What you don't see is what I destroyed when I pulled this plant up. The root hairs. Every single root would have had hairs coming off of it. They are microscopic. You cannot see them with your naked eyes. You would need a microscope to see them. They are 1 cell thick. And that single cell thickness of the root hair makes it extremely permeable to water. And so all over these roots, millions of root hairs would have been on it. And I have just destroyed most of them when I yanked it through. Now there's still some there. I just can't see it with my naked eye. I would need a microscope. But what that would mean is that if I planted this Echinacea back, it would show serious wiltage for a while. It would have a hard time keeping up with drinking enough water to keep up with its transpiration rate through its leaves. So what that means is that when I transplant this, if I were to plant this somewhere again, which, I mean, it is healthy enough, I probably could give it a shot, I would need to water it excessively at first because I have damaged so many root hairs. The other thing I could do is to cut the plant back. It seems counterintuitive, like surely you would want to have a lot of leaves on the plant because that's photosynthesis. But a lot of leaves means a lot of transpiration. So if I cut off definitely cut off the flowers, there's no need for that right now. Cut back the leaves so that it's got maybe a third or less of the leaves. That would allow the plant to do enough photosynthesis, but reduce the transpiration in the plant, which would give the roots time to repair itself and grow. If you want to protect this plant, you need to protect its roots first before you focus on protecting its leaf growth, etc. So this is a shot of the whole plant. If you take a look at it, it does give the impression that the roots are actually a very small component of the plant. And in several shallow rooted plants, that might be true. Now, to be fair, I did break a lot of the fibrous roots off when I yanked it out of the ground the way I did. But even so, it does appear that the majority of the plant is above ground. That's definitely not the case when we take a look at trees. So here we can see a cherry tree. It's about 5 years old. Despite its size, it's grown very quickly. It is almost at full size in terms of height. It's a dwarf, but it's going to get thicker over time. So that's my cherry tree. But whatever you see on that cherry tree, a good estimation is that below ground, there's about 3 times the volume in roots. Trees are amazingly good at resisting, established trees I should say, are amazingly good at resisting drought sessions for quite a while because their roots go deep, they go far, they go wide. There is actually more tree below ground than there is above ground. All right, so let's sum up what we've learned so far. Water is essential to life because it is the universal solvent. It is such a good solvent because it is polar covalent. That means that water molecules are highly attractive to itself and can pull itself along and be cohesive towards itself. But it is also fairly attracted to other molecules if they have any slight charge to them or full charge even. And so it can dissolve a lot of molecules in them. A lot of complex molecules can dissolve into water. And therefore, you can get a rich mixture of chemicals for running and driving the chemical reactions of life. Because water is essential, you need to make sure that your plants have an adequate supply. The supply of water generally enters the plant through the roots, but they are very thin structures that a lot of it you don't see because they're tiny microscopic root hairs. The water flows up through the plant against the pull of gravity because of its cohesive nature to itself, and that cohesion as it's pulled up through the plant is driven primarily through the process of transpiration, which is the evaporation of water from the underside of the leaves through the holes known as stomata. The challenge that we have in the garden is that some plants are more resistant to drought than other plants, and most of the plants that people want tend to need a lot of water. Things like your vegetables, for example, they are extremely water-filled features that you're going to have. Like a tomato is mostly water, so it shouldn't be a surprise that those plants require large quantities of water, because not only do they need the water flowing through them, they're going to produce products that store water in them. So we have to figure out ways of reducing the amount of water you need to pour onto the land, because it isn't necessarily a sustainable practice to do that. Here in southern Ontario, we are very close to the Great Lakes. We do not have a shortage of water technically, but it does take energy to treat and process our water. So you don't want to waste it, even though you have a good supply of it. climate change is adding to the problem. In addition to the fact that some areas have less rain in southern Ontario and less water in the ground in southern Ontario, the rising temperature means that water is evaporating from the grounds at a higher rate than it did in the past. So even if you are not getting less rain in an area, you may notice that your plants are suffering more water loss because the transpiration rate is higher and the evaporation from the ground is higher. So what can we do to protect our plants in a way that is sustainable and that keeps up with the changes that we're seeing with climate change? The first thing is to find ways to adequately use the water in your garden if you have a water shortage in your area. So many areas, people are starting to put in their rain barrels, etc. So when it does rain, any rain that they don't use right away can be stored in barrels and then used later on. So that is one technique. In my area, I have not felt the need for a rain barrel at this point in time. We have an adequate supply of rain, to be honest. I live on clay soil. I also lay on technically a riverbed. Unfortunately, Toronto sank a lot of our above ground rivers. It's underground. And so even though you don't see a river in this area, underground that river runs, and the water table therefore is high, and there's moisture coming up out of the ground. So I actually have a fairly good supply of water most of the time. I still do, however, have to spot water certain vegetables because if they're in their young stages, if they're seedlings, they may need some assistance. They can't go more than maybe 3 or 4 days, especially if it's hot, without a little bit of water at least. So storing your rainwater may be something you need to do. The other thing is to do something that I have not done an adequate job of in my garden, and that is to protect the ground so that evaporation is reduced in your garden. That's where your mulches come in. Now, mulches require you to buy mulch or find a source of mulch, which is why I have not put in the amount of mulch I should. I'm strategically attempting to put the mulch in. But there are some things you can do if you don't have mulch in your garden, or if you're in the process of getting the mulch in the garden. And that is to screen the ground using the plants. The plants themselves can be the mulch. So if we take a look at this area of the garden behind me, in this area of the garden, you can see that the plants are very densely packed together. What that means is there's actually one patch right there where I removed some rocks recently that is bare, it is exposed, so the evaporation rate right in that area would be high. But everywhere else where you see densely packed plants, there would not be a lot of evaporation or at least it would be reduced, because the leaves are actually shading the ground. So if you can shade the ground, you don't necessarily need to cover the ground. That would be the first thing I would say. But ideally, I would have put a mulch in there as well. And so over time, I'm increasing the number of sections of the garden that have mulch. But mulch does cost. And so it is a process over time that's happening because my garden is fairly large for the city. The other strategy that you can use is to use living mulches. So there are a number of what we call cover crops, which you can buy from seed companies. Clover is a good example of a cover crop. They are tiny, tiny crops. Technically, this right here below me, this patch of thyme, would be considered a cover crop. It's a very short creeping plant that covers the earth. It's easy to rip out if I want to put a plant in the area. And so you can see I've ripped out a patch right here, and I've been planting some Swiss chard in it. But it covers the earth very nicely, and therefore it keeps the moisture in it. Okay, the final tip for dealing with, you can see actually I do have mulch in this area, but the final tip I could say for trying to conserve water in the garden is to be strategic about where you place plants that are high demanding in the water. So for example, cucumbers do demand a fair bit of consistent watering. If it were to go dry for a few days, or a week it didn't rain, I would need to water the cucumber plants. But what I have here is I have them planted in a container. That allows me to say, look, I can just water this container, and the cucumber plants would be taken care of, and I'm not going to be wasting water on watering the rest of the garden this way. So there are a number of types of containers. I will say that I really like, for Southern Ontario, using whiskey barrels or wine barrels. You can get them from local distilleries. They're a waste product of the distillery process. They have to replace their barrels from time to time. They are waterproof when they first get them. They do age and they get less waterproof, but what it means is water retains very well in them. They last about 25 years. They are you're reusing a product here in Ontario when you do that. So if you can use whiskey barrels, I'm actually a big fan of them because you're reusing the wood that would otherwise get thrown away. The wood is of a very high quality. It makes a container that is very good at water retention. It's nice and deep, which means it creates a nice little microclimate for your plant, and you can enrich and amend that soil. It's even big enough that if you wanted to plant a small tree in it, you can actually get away with that. And it creates the ability in the garden to create microclimates very quickly so that water intense needing plants can be clustered. And unlike ceramic containers, because there are some beautiful ceramic containers, they don't crack in winter. And fiberglass, also I found those containers, plastics, fiberglass, they all crack over time. But the whiskey barrel, they genuinely do last a very long time. Okay folks, I hope you enjoyed today's lesson on water in the garden. There's a lot we could learn about water in the garden because the garden runs on water in many ways. After soil, the next ingredient is water. So I hope you enjoyed it, and I hope it has inspired you to grow something. Even if the only thing you did was to grow a flower, that would be lovely. See you later. Bye.